Pi. I know you all love to eat it, but how do we use it in math? Well, pi in math, you know the digit pi, but what is PIE, the principle of inclusion and exclusion? Well, this is a form of overcounting. And overcounting is the process of counting more than you need and subtracting off the parts which don't belong. The principle of inclusion and exclusion is an organized way of dealing with these overlapping, subtracting for them, but sometimes we subtract for extras. So essentially, we're going to explore how to use this in this video. Let's start off with an example. Mark and George are playing a guessing game. George randomly chooses two numbers between 1 and 25. Mark then asks George if exactly one of the two numbers is divisible by 7. George truthfully answers yes. Mark proceeds to guess one multiple of 7 and one number that is not a multiple of 7. What's the probability? Mark guesses at least one number correctly. At least one number correctly. So it could be two numbers correctly, it could be one number correctly. Okay, so George truthfully answers yes when Mark asks him if one of his numbers was divisible by 7. And not just if one of his numbers, if exactly one of his numbers. So what are the multiples of 7 between 1 and 25? 7, 14, and 21. Those are the multiples of 7 between 1 and 25. Okay, so Mark asks if one of the two numbers is divisible by 7. George says yes. Okay, so exactly one of them are divisible by 7. And from the remaining numbers, 1 to 6, 8 to 13, so on, all the numbers that are not divisible by 7, essentially because George says that exactly one of his two numbers are divisible by 7, one of them must be divisible by 7, and one of them must not be divisible by 7. Okay, so Mark is going to guess a number that's divisible by 7 and a number that's not a multiple of 7. What's the probability? Mark guesses at least one number correctly. At least, not exactly, at least. So what is the probability that he guesses the multiple of 7 correctly? There's 3 multiples of 7 less than 25. So there's going to be a 1/3 chance of picking the multiple of 7 that George was thinking of. So if George was thinking of 7, for example, then if he randomly picks a multiple of 7, he has a 1 in 3 chance. Similarly, if George picked, let's say, 21, again, a 1 in 3 chance of picking if you randomly guess a multiple of 7. So 1/3 chance, multiple of 7, correct. Okay, now what's the probability he guesses a number that's not a multiple of 7 correctly? Remember how George must have a number not divisible by 7? And Mark guesses a number that's not divisible by 7. There's 25 numbers. 3 of them are divisible by 7, as we see here. So 25 minus 3, 22 of them are not divisible by 7. Okay, so if 22 of them are not divisible by 7, then let's say George picks something like 8. Now Mark will randomly guess one of these 22 numbers, and he's going to have a 1 in 22 chance of guessing the number. So number not mult 7. 1 in 22 chance. Okay, so he has to guess at least one number correctly. So is it just 1/3 plus 1/22? No, because we are overcounting a little bit. And this is where the principle of inclusion and exclusion is going to come to the rescue. So what if he guesses the multiple of 7 correct and the number not a multiple of 7 correctly? So let's explore this with a Venn diagram. This is the 1/3 chance of multiple 7 correct. So this is the probability he guesses a multiple of 7 correctly. Now, this is the probability he guesses the number not a multiple of 7 correctly. But there's this probability in between we're overcounting. So we can't simply sum this probability with this probability over here. Because there's just some part in the middle where both the multiple of 7 are correct and the number was not a multiple of 7 that we're overcounting. So what's the probability the number not the multiple of 7 was correctly guessed and the number not a multiple of 7 was correctly guessed? That's just, well, a 1/3 chance of multiple of 7 correct, 1/22 chance of not multiple 7 correct. So we multiply them to get the probability that both guesses are correct. So 1/66 is this inside part. And as you can see, it's being counted by both the multiple of 7 correct and not multiple of 7 correct. It's overcounted. So what we do is 1/3 plus 1/22 minus the overcounted part, 1/66. This is just 22/66 plus 3/66 minus 1/66. That's 24/66 equal to 4/11. So 4/11 is our answer. Okay, let's now solve this problem. How many different ways are there to arrange the letters in the word lollipop if each of the L's must be next to an O? This is interesting. This seems like a word rearrangement problem, not PIE, doesn't it? Well, let's write out our letters. You know how I mentioned in the previous video the strategic strategy of writing out letters. So lol, LOL, li, LI, pop, POP. Okay? These are all the letters of lollipop. Okay, but it says each of the L's must be next to an O. Okay, so we've got 3 L's, but only 2 O's, right? 3 L's, but only 2 O's. Each of the L's must be next to an O. So we can't just pair them up LO, LO, because then there's going to be an L left over. What does that mean? We've got less O's than L's, but somehow each of the L's are next to an O? Oh, that means that one O must be next to multiple L's, right? Because if we have something like LOL, where one O is next to multiple L's, then that has one O, but 2 L's are satisfied. So if we have something like LOL, where both the L's are adjacent to the O, then we can also have something like LO on the side. So as you can see here, 2 L's are adjacent to the first O, and the last L is adjacent to the second O. So if you remember from word rearrangements, we can just group these together. LOL, one group. LO, one group. And LOL, let's make that different colors. LOL and LO. LO. And then these 3 letters are just individual letters. They don't have to be grouped with anything. Now this is like a word rearrangement problem. We've got 1, 2, 3, 4, 5 things to rearrange. So 5 factorial over 2. And then, because 2 p's, so divided by 2 factorial. This is 120 divided by 2, 60. But this has LO as LO. What if it's OL? What if it's LOL is still one group, but what if this part is now OL? And then there's, of course, IPP still to be rearranged. It's the exact same thing. 5 factorial over 2 factorial, 60. But notice that LOL only has one arrangement. It's symmetric. And we can't have something like OLL, because then the O is not adjacent to both the L's, which is what the condition says. Each of the L's must be next to an O. So we can't just rearrange this to OLL. The O has to be in the center, 2 L's on the outside. So only one way to rearrange this part, but the purple part has 2 ways to be rearranged. Okay, so 60 and 60. So is your answer just 120? Key thing to check is always whether you're overcounting anything. So are we overcounting anything between these 2 cases? Hmm. LOL, OL, LOL, LO. Is there any way we can overcount? Oh, wait. Look here, we've got LOL, OL. This is with OL. Now, LO, what if we just move this part to the beginning? L, OL, OL. L, OL, OL. But this part has the purple part before the green part, and this part has the green part before the purple part. So we counted them as different ways, didn't we? Right? We counted them as different ways because the purple part and green part were arranged differently. But they seem like the same thing. LOL, OL, LOL, except this part has LO as the first group, and this part has OL as the last group. Oh, so it seems like whenever we've got LOL, OL, the string together, we can break it up into the two groups as LOL and OL, or LO and then LOL. So we're overcounting all the cases that contain the substring LOL. So how many cases are there that contain LOL? And then of course IPP. These are the cases we're overcounting. So we're going to do a big minus there. How many arrangements of a group IPP? Well, there's kind of four things, right? So times 4 factorial over 2 factorial, which is 24 divided by 2, 12. So we're overcounting this case, right? It's counted here and here. So we subtract it off because we counted it 2 times, we only want to count it once. So our answer is just 120 minus 12 equals 108. And luckily for us, we're not overcounting any other case, because any other case, like for example, if we had LOL, or LOL, here, for example, and then we had maybe something like OL, these are different cases. They're not the same, right? Because LOL, OLL, they're not the same thing. So luckily, there's nothing else that's overcounting between these cases. Just 12. So our answer, 108. Key idea here, 2 cases, of course. Grouping the LOL, the strategy we learned in word rearrangements chapter. And then noticing that there's going to be some cases overcounting. So we subtract 12 to get 108. A great problem. But what about, essentially for 2 sets, what principle of inclusion exclusion states is that what we can do is just take the possibilities for, let's say, A1 and A2 happening. So let's say you're trying to find the probability that 2 sets or 2 things, A1 and A2, both happen. We just find the probability A1 happens, then the probability A2 happens, and subtract the probability where they both happen. And we've got something similar for 3. Essentially, to find the probability 3 things happen, we find the probability of each individual thing happening, then subtract the probabilities where 2 of the 3 things happen, and add back the probability where the 3rd thing happened. To intuitively understand this, let's draw a Venn diagram. Got a 3 Venn diagram here. So let's say this is A1, A2, and A3. Okay? So this represents all the possibilities where A1 works. This represents all the possibilities where A2 works, and this A3. So we're overcount. If we're trying to find all the possibilities within this Venn diagram, we just add up A1, A2, A3. We're overcounting the regions in the middle. So we're overcounting this, we're overcounting this, and this. Okay. But then the thing is, notice how the center region, first it's counted once as part of A1. It's also counted as part of A2. It's also counted as part of A3. Then it's subtracted as part of the intersection between A1 and A2. It's subtracted as part of the intersection of A2 and A3. And it's subtracted as part of the intersection A1 and A3. So it's added 3 times, subtracted 3 times. But we're trying to count everything exactly 1 time. So we add it back. And that's where this kind of comes from. Let's now try an interesting example from the AMCA that uses pi for 3 different things. 5 different awards are to be given to 3 different students. Each student will receive at least 1 award. In how many ways, different ways, can the awards be distributed in? Now, if you know stars and bars, you might think just to use stars and bars. But the reason it doesn't work is because the awards are different. If it was same, then stars and bars could work. By the way, we'll cover it in a future video if you don't know what it is. Each student will receive at least 1 award. This is kind of the main constraint that makes the problem a little tricky, right? Each student receives at least 1 award. So let's not focus on this condition for now. Let's just see what would happen if we're just consider this problem. 5 different awards. Let's say award 1, award 2, award 3, award 4, and award 5. These are the awards. Okay? And these are the students. A, B, C. Okay, so how many ways are there to do this? Well, each award can go to A, B, or C. Each award can go to each of the 3 students. 3 choices for the first award, 3 choices for the second award, 3 choices for the third award, 3 choices for the fourth, and 3 for the fifth award. It's 3 to the power of 5. That's 243. So, ignoring the constraint where we could just have anyone get any award, that's 243 different ways. Okay, so now what? Now, what about the cases where maybe a student receives no awards? Because if any student receives no awards, then we're overcounting that case, right? Okay, let's see. What happens if student A receives no awards? Well, then the 2 remaining students must receive the 5 awards. Now, each of the 5 awards only has 2 choices, to student B or to student C. So there's 2 to the 5 equals 32 ways where student A, no award. Okay. Now, what about if student B has no award and student A and C get all of the awards? That's also 2 to the 5 equals 32. Similarly, if student C gets no awards, then student A and B, each award will have 2 choices to go to student A or B. Again, 2 to the 5 equals 32. Okay, this is getting a little bit messy, right? So we're not really sure what we're counting, what we're not. Let's draw a Venn diagram. Venn diagrams always make things a lot easier. So student A, no award. This was B, no award. And this was C, no award. Okay, so student A, no award. Student B, no award. Let's do a different color for that one. Student B, no award. Student C, no award. Okay, so student A, no award, we already found that there's 32 ways for that to happen. That's this red circle over here. Similarly, all of them are 32. We already discovered, right? They're all 32. Now, what about the case where student A and student B, let's say, don't get an award? That's this region over here. So if student A and student B both don't get an award, then student C gets all 5 awards, A, B, C, D, and E. How many ways are for this to happen? 1. So there's 1 way student A and B don't get an award. Similarly, there's 1 way students A and C don't get an award, and 1 way students B and C don't get an award. A would have all of the awards then. Okay, so that's cool, but what about the case where all 3 of them don't have any awards? That's not possible, right? Because we're giving 5 awards to 3 students, so that's not possible. So this inside region is basically 0, so we don't have to worry about it. So in total, how many ways are there where a student gets no award? Well, if a student gets no award, then 32 plus 32 plus 32. So what we're counting is, this is the complement, right? Where some student receives no awards. Some student, 0 awards. This is 32 plus 32 plus 32, each of the 3 big circles. And then we subtract each of the overlapping regions. So this, 1, 1, 1. So we subtract 3. Oops. Too thick. Minus 3 equal to, this is 93, right? And we found that the total number of cases was 243. So what we're going to do is 243 minus 93 equal to 150. So 150 is our answer. So just to review, essentially what we did is we found the total number of ways to divide these 5 distinct awards amongst the 3 students, 243 ways. And then we did complementary counting. We looked at all the ways where a student has no award. We found that a student A has no award 32 ways, B no award 32, C no award 32. 32, 32, 32. But there's some overlap where both A and B didn't get an award, B and C didn't get an award, and A and C didn't get an award. So we subtracted that overlap. So 33 is the total number of ways where there's a student who does not get any awards. And then we did complementary counting, so 243 minus 93, 150. So this was a good example where we combined complementary counting and pi. Okay, so next off, we have stars and bars. I just mentioned that earlier. Stars and bars is where instead of distributing distinct objects, identical. This is a really, really clever trick. A really, really clever trick that we can use for using these stars and bars problems very easily. Let's explore that right over there.